Hi, we have been discussing about different kinds of concepts in Verilog. We discussed about data types, operators, different kinds of operators, compiler directives, system tasks, assignments, blocking and non-blocking, and different kinds of procedural blocks like initial and always block, and various kinds of constructs like if, else, task, and functions. Now you know too many things as bits and pieces, the overall language. And if you look at the language is huge, there are so many constructs like this. Now it's time for you to understand how to make use of all these features to write the source code. You write source code for two main purposes. One for simulation, the other one for design. Now look at this, there are two different things. One is design, the other one is test bench. You use test bench mainly to verify the design. But these two things basically demand two different styles. When it comes to test bench, let's look at test bench. It's mainly for verifying the design, right? So the test bench is going to generate stimulus, and then during simulation, you are going to look at all the output. That's how you are going to verify the functionality. But while writing test bench, you don't really need to worry about synthesis. After verification, basically, you are going to leave the test bench alone. You're going to use only the design part. So when it comes to writing test bench, you can use all kinds of constructs in the language. There is no restriction, and you don't really need to worry too much about the style. The style wise, it would be more of writing software programming. Now let's look at the design. That's where synthesis comes into picture. Whatever the source code that you have written for the design, eventually it has to be synthesized. So there are some restrictions. You cannot use all constructs in the language. You have to use only synthesizable subset. Then you really need to understand what is a common synthesizable subset that can be used across various kinds of tools in the market. There are EDA companies like Mentor, Synopsys, and Cadence, and they have different kinds of tools. There may be variation with respect to synthesizable subset, but you have to find a common subset. See, whatever the source code that you have written, that should be able to work fine with any kind of tool. That's called tool-independent source code. So synthesizable subset, one of the important things you need to understand. And the other thing is coding style, how you want to implement the hardware. For example, multiplexer, basically it's a parallel logic, so you have to use case. But when it comes to priority encoder, we want to use if else. If else will assign the priority to inputs. And FSM has its own coding style. So you need to understand the coding style. Two important things you have to understand for synthesis. One is synthesizable subset, the other one is coding style. That's what I'm going to explain in this module. All right. This is our proprietary material. In this video, I'm going to explain how you can implement different kinds of logic, sequential devices, and how you can avoid unwanted latches when it comes to implementing combinational logic. So initially we are going to look at like how to implement different kinds of logics like sequential devices and combinational logic. And while implementing combinational logic, how we can avoid unwanted latches. And then finally, we will also look at how to deal with operators, how to specify registers in Verilog. In RTL, we use always. So initial is non-synthesizable. That's meant for test bench. Okay. While defining the block always, you say passage clock in the sensitivity list, it's going to infer the sequential device, which is nothing but flip-flop. Always remember this. If the sensitivity list is going to have passage clock, obviously it's going to infer flip-flop. Now let's look at this example. Here, always at passage clock, begin, end. This is where you define functionality. So here, how this is going to implement the register and combinational logic, you need to understand. Whatever you define at the right hand side, that will be inferred as combinational logic. So here, there are two variables, x, y, they are output, and the right hand side implements the logic. Here, what really matters is, are you using non-blocking or blocking? But the coding style wise, we always use non-blocking for sequential device. So here non-blocking means both the statements will be executed at the same time. So X should get the value. At the same time, Y also should get the value. So X and Y will happen at the same time. Now you think about the logic, how it has to be input. A and B has to be calculated. At the same time, C or D should be calculated. So A and D, it goes to a flip-flop. At the same time, C or D, that also goes to another flip-flop. This is X, this is Y. So you get two flip-flops because this is non-blocking. And you are getting two flip-flops for the output because you have clock. Logically, if you look at, whenever clock edge happens, X and Y should get the value. And how the value can be produced? The right-hand side equation defines it. This is A and B, this is C or D. So for X, there is an AND gate at the input. For Y, there is OR gate at the input. All right. Resource sharing. Look at this example. Always at select A, B, C. And if select is high, output is A plus B. Else, output is A plus C. Here, do you need one adder or two adders? Here, actually, with one adder, you can implement efficiently like this. So here, adder is more expensive in terms of gates. So you are going to use even macro cell also. So you always need to think like how best you can realize the logic. Here you look at, you get the same output. Here also, A plus B happens, A plus C happens, and then finally, we choose one of the results. So obviously the Z is going to be either A plus B or A plus C. So if you are not experienced, this is how you try to realize the circuit. Look at this possibility. But this is not really good. You can also implement something like this. Here, I am choosing the inputs through multiplexer. So I'm choosing between B and C, right? And that's going to be X. And then A plus X will always be performed. So here, if select is high, B will be there. So obviously A plus B will be performed. If select is going to be 0, then the addition is going to be A plus C. So both are same. Here this is good because one multiplexer, one adder, but here two adders, that is the concern. It's going to be very expensive in terms of gates. Some synthesis tools can perform this kind of optimization automatically. But if you are experienced, you can also think of writing code like this. That will always infer this kind of logic. Look at this. Instead of writing code like this, I want you to write code like this. You visualize how many resources needed and how to save the resources. I don't want to go with two adders. I want to go with only one adder. And this is the better way of writing the code. Select A, B, C. If select is high, X is going to get B, else X is going to get C. And then I'm going to use X to perform the addition. Assign Z equal to A plus X. Here these two are concurrent. So it's going to produce X, and then based on the X, it will perform the addition. That's how it works. Thank you. Thanks for watching this video.